multivariable calculus. This is a course, typically a third course in the sequence of calculus. And third parts don't usually have the best rep. There is something called the third part curse. And there's many third parts that are terrible out there. But then there is also many third parts that are really good. And I'm hoping that this course is in that group, in that there is a lot of like really cool things happening in multivariable calculus. So what is it that we're going to be doing in multivariable? It is just multivariable calculus. So you've learned a lot of calculus that happens in functions of one variable. Okay, so if I have a function y equals f of x, then we've learned how to draw the graph of a function like this. And we're going to start by doing basically the same thing, except that now we're going to be talking about functions of several variables. Mostly our examples will come from functions in two variables, x and y. And for those, well, there will be graphs, but now maybe this function was defined in some interval between a and b. But immediately things get a lot more exciting when you have more variables to talk about, because the domain of your function doesn't have to be, it's not an interval, it could be a rectangle. That's the easiest that it can be. But maybe our domain is some sort of like, some sort of shape in the xy plane. Let me try to do a better job at drawing a circle. And then the graph is going to be some surface above that. So suppose that the graph is, I don't know, some paraboloid like this. Okay, something like that. Now, what kind of things did we learn? What did we do to describe functions in calculus 1, say? Derivatives, integrals. Well, what were we trying to figure out when we took derivatives of functions? We were actually trying to figure out what is the growth, what's the rate of change. That was the first name you might have learned for a derivative, is the rate of change of a function. That is because some functions are not easy to graph a priori. You don't know what the graph is like, but by looking at the rates of change, then we can try to sketch graphs. So we did learn how to do that. So at some points, we learned how to take derivatives, but just to understand the rate of change, we also understood how to draw tangent lines. That tells us what the rate of change is in a graph. So if I have some other point here, now I also want to know what is the rate of change there. But again, it all gets a lot more exciting because I can trace in one direction, but there is other directions where the rate of change is very different. And in every direction, the rate of change is different in this graph. So there is now infinitely many directions that I can take derivatives in. And then we did take a tangent line using those rate of change. But now I can actually do tangent lines, but there's also tangent planes. So I can take a whole tangent plane at that point and use that tangent plane to do very similar things to what we did with a tangent line, approximate values of a function using a tangent plane. There's somebody here who was in my linear algebra class just a few minutes ago, and we saw an example of that, how to use a tangent plane to approximate the values of the square root of x squared plus y squared, for example. We can do that. Now, what did we do also with derivatives? By knowing where the tangent line was flat, horizontal, what did that tell us about a function if the tangent line was horizontal?
It wasn't growing?
It's not growing, or it's sort of like there is a change on the growth of some sort. It could be that the growth changes. It can be like a inflection point. There are several types of things that can happen. When the derivative is 0, we call those critical points. So for example, in here, there is a critical point right about there, and that tells me that it's, in that case, a local minimum. So we want to do that kind of thing also in 2 dimensions, but now there is a lot of possibilities. For example, here, you can see that there is something going on in that direction, very different in that direction, but there is a point here where something very special is happening, which is that the tangent plane is parallel to the xy plane. So that tells me that there might be a local point, a local max or a local min, some extreme point happening right there. So whenever that happens, we might find some local extrema. So we're going to also spend a bunch of time trying to figure out how to do that in several dimensions. Also, integrals were mentioned. What were the integrals? What's the point of an integral? Define the area under a curve. So if I draw, we have a lot of colors here. Let's do blue. So if I want to know what is the area under this graph, I can take an integral and figure out what is the area under that graph. What is an integral going to do for us in 3 dimensions? Volume. So now I can try to do an integral, but now it's also more exciting. Like now I'm going to do an integral, but the region that I'm going to integrate over, it's not an interval anymore. It's going to be a circle. And over that circle, I'm going to try to figure out what is the volume of that whole paraboloid. Okay, so those are going to be integrals. Now, there is other things. Did you ever compute the length of a graph in calculus 1 or 2? So sometimes that is seen in calculus, where you can also compute not the area, but the length of this piece of the graph. We can do also the same thing here. I can take a path, say to the top, and figure out what is the length of that path. Why would you do that? Well, if you are an air company, you might want to travel from Madrid to Boston in the shortest way possible. So you want to figure out all the possible paths to get from point A to point B and figure out what's the shortest path. Those are called geodesics. And the geodesics on Earth, there are geodesics on every surface. So we're going to be interested in paths that minimize distance between 2 points. How do we know what the distance is? Well, we're going to have to figure out how to compute what we call line integrals, how to get from here to here, and what is the length of that whole line. So those are some of the things we're going to see. And in fact, it gets even more interesting. Once you know how to do line integrals, then we're going to see at the very end of the class some of the most interesting theorems in all of calculus and some of the very first theorems that are really something else in, say, analysis, where we have things like Green's theorem, or there's a number of these theorems that tell you that if you do an integral, a certain integral, a line integral along a path, it turns out that that is related to the area that the path is enclosing. So we're going to be able to compute very intricate areas by doing an integral along a line. And similarly, there's going to be theorems that are sort of like extensions of this to higher dimensions that tell me that if I have some surface, there's going to be a way to compute the volume. That's 3D, so we're missing an exit there. We're going to be able to compute a volume of the inside of this object by doing some sort of surface integral. We're also going to be able to compute integrals along the surface. So I'm going to be able to, take some like curved piece of an object and compute the area in there, and then use those surface integrals to actually compute the volume inside through some very famous theorem. Okay, so now all of that is also a way to tell what is happening, how are we going to understand how to do a graph and like what the behavior is of some of these functions that we're going to discuss. And as I said, all of this, we have a point here, then we're going to take derivatives, and we're going to find planes in here and find volumes under graphs of this sort, all with, because there's a lot of different applications. Most functions out there in real life do not depend on one variable. They depend on many, many, many variables. So this is a little step closer to actually modeling real life. So in this class, we're going to cover as I said, sort of like already, we're going to start by trying to understand how to work with three-dimensional space. Ideally, and in many cases, all of what I'm going to say, it extends to more variables than three. But for just to fix ideas, we're going to mostly work in 3 dimensions. We're going to take derivatives in 2 or more variables. We're going to do double and triple integrals. A double integral would be, for example, the volume under a graph, but a triple integral will be some other volume where the object we are enclosing is not really just a graph, it's some composite of graphs, and then we're going to try to figure out what is happening inside it, some sort of volume. We're going to talk about vector functions, and then we're going to talk about parametric curves. That's how you draw a path on a surface. To draw that path, we're going to have to parametrize that curve and then be able to do integrals along those curves. Those are the line integrals I talked about. And then we're going to talk about surface area and surface integrals, which will lead to those big theorems at the very end of the class that I mentioned, like Green's theorem. Today, though, we're going to concentrate on three-dimensional space. Do we have any questions so far about what I've talked about? All right. So just to, for notation, this is the symbol mathematicians we use for the real numbers. That for us, for the time being, the real numbers are just all possible decimal expansions. If we had repeating decimal expansions, those would be rational numbers. All the decimal expansions, those are the real numbers. Then R2 will be the real Euclidean plane. R3 is the real Euclidean space. And if we want to get creative, then for any n bigger or equal to 1, our n will be n-dimensional space. So now we're going to be working mostly in 3D. It's a lot more difficult to plot things in 4D, but we'll try at some point to imagine once we have a 4-dimensional object, what does that look like? So our old axes were x and y. And now you have to think that we're going to be looking at that x and y from up above. So I'm going to put the x-axis here and the y-axis here. So this is 1 and 2 and 3 and 1 and 2 and 3. So the positive axes are here. And then we're going to jump to 3 dimensions by putting here z-axis. And again, the upwards is the positive side of the z-axis is going up out into space. All right. So let's try to plot 2 points in 3D. It's difficult to draw things in 3D, but hopefully by doing it enough times, you're going to get some used to this. So I'm going to plot the point 3 minus 2, 1 first. So let's do 1, 2, 3. It goes up to 5. So I'm going to put a 5 here. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 in there. And down below. 1, 2, 3, 4, 5. So how do we do this? Let's plot the point 3, 2, minus 1. So this is the point, the x-coordinate is 3. It's minus 2 for the y-coordinate. So here is minus 2. So I can go and draw a, what doesn't look, that doesn't look quite perpendicular. So let's try to do a better job here, like this. And this point, that point down there would be the point 3 minus 2, 0. And then I have to go 1 up. So if I go 1 up like this, you can imagine that there is some sort of like parallelepiped being drawn. And then the point that I want is all the way here. This is the point 3 minus 2, 1. Okay? So where is the point minus 2, 3, 5? So minus 2, 3, 5, I have to go backwards. Here is minus 1 and minus 2. And 3 is here. So I first draw sort of the projection of the point and the xy plane, and then draw, go all the way to the third dimension by drawing some big box, just to complete the box. And that drawing the box allows me to sort of like, for my brain to sort of imagine where this point is. It's like way in the back and way below. So here is minus 2, 3, minus 5. That makes sense? Yes?
How do you know which is which? Like, how do you know x is like 3, or how do you know z is 2?
Oh, good question. So these points are always the x, y, z coordinates. I should have said that by thinking here, is that when we talk about the R2, our points this is the set of all possible pairs x, y, where x and y are real numbers. Okay, so our points are going to be, the first coordinate is the x-coordinate, the second point is the y-coordinate, and in R3, our points are going to be 3 coordinates, x, y, z, where x, y, and z are, we mathematicians, we use this symbol to denote it belongs. X, y, z belongs to the real numbers. And similarly for n-dimensional space, x1, x2, up to xn, where every xi is a real number, that's how we denote points in n space. So in particular, that's why 3 minus 2, 1 is a point where the x-coordinate is 3, the y-coordinate is minus 2, the z-coordinate is 1. Any other questions? Okay, so what about, what kind of a surface in R3 is given by z equals 3? Anyone? It's a plane. Can you sort of describe it with your hands?
It's like an infinite flat plane at like z of 3.
Yeah, yeah. We're going to do a lot of like hand waving in this class just to try to describe what's happening. But that is exactly what it is. It's a plane that is going to be parallel to the xy plane. Why? Before I try to draw anything, let me try to describe the points. The points in this surface, I'm going to call the surface S, are going to be points where z equals 3. I'm not giving any more information, so that tells me the x and the y are free to move around the country. So this is x, y, and the z is 3. So I can fix it to be 3. And this, since in the absence of conditions, x and y can be anything I want. So x and y are any real number. That symbol over there that I keep drawing is that symbol. It belongs, or it's just in this other set. Okay, so what is that? Those are points. Let's just now try to draw a few of those. So this is z equals 3 is here. And then this is the x coordinate, and this is the y coordinate. And for example, 0, 0, 3 is in the plane. It's in this surface. We don't know yet what it is, but it's here. What about 1? It's easier to draw the ones with x is 0. So 0, 1, 3. That's in the plane. That's in this object here. 0, 2, 3. That's here too. What about 0, 0, 2? No, because z is not 3, so that's not there. What about 1, 0, 3? So 1, 0, 3 would be now here. That point belongs. And 1, 1, 3, and 1, 2, 3, all those belong, so they are in the plane. And you can see now that there are 0.02, so actually what I get is an entire plane, because it's every number that z is equals to 3, and that is a plane that is parallel to the xy plane. Okay. What about y equals 5? I saw a hand gesture over there. So what is it?
Vertical.
It's a vertical plane that passes through, give me 1 point.
Y equals 5.
With any point with y equals 5, really. Again, I can describe all the points in the plane. They can be anything. Y has to be 5, and they can be anything. So if you try to just sketch that, we have y equals 5. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is x, y, z. 0, 5, 0 is in the plane. That's that point right here. 0, 5, 1 is in the plane. 0, 5, 2 is in the plane. 0, 5, minus 1 is in the plane. But if I move the x is 1, and then that's some points that are sort of over here. Just like move them over a little bit. Those points are also in the plane. So it's a vertical plane that is parallel to what plane?
The XZ plane?
To the XZ plane. So it looks sort of like this. That plane. Okay? And as I said, we can represent that as a set like this, where x and z are just any real numbers. As long as the y coordinate is z, is 5, then that's the answer. Okay? The surface in R3 given by y equals x is a point, a line, a half of 3D space, a plane, Superman. All right. So it's points where the x and the y have to be the same quantity. So it has to be points x, y, z, but y, I already know what it is if I fixed x. So it has to be x, x, and then any value for z. All right? So now x and z are any real numbers. How do I figure out what that is? I can start by figuring out what happens when z equals 0. So I have at least what is happening in the xy plane. So in the xy plane, if z is 0, it's all the points that are x, x. So the y and the x are the same, and that is that line over there. Okay? So that line keeps going that way. This will be useful in the future. That's what we call a cross-section. Our surfaces in 3D sometimes are very difficult to figure out what they are, but what I can do is slice them with a plane and then figure out what is the cross-section with a plane. In this case, it's a line. What happens if I take the cross-section with z equals 1? It will be all the points x, x1. So it's another line, but it's a line that goes like the other one, but higher up. And if I put z equals 2, I get a cross section that is another line, and it's just a line like that. So it's sort of like a flag, but except that it just keeps going in every direction. Well, it almost looks like the American flag. So it's a plane like that. Okay, so it's a plane that is diagonal and it goes through the y equals x line, but it's an entire plane. And it's just a plane. We're not yet drawing anything that has actual sort of volume. This is just one plane. What about this surface in R3 that is given by x squared plus y squared equals 1? What does that look like? What's that? I didn't hear. A circle? So it's a circle if I forget there is a z, but we're in R3. It's a cylinder because what happens here is that the x and y coordinate have to satisfy the equation of a circle of radius 1. So that is the cross section with z equals 0. But now the z value can be anything we want. So if I go to the z equals 1 plane, I get another circle. It's the same circle, but you get the idea. And then it's just going to look like this. It's just going to be an infinite cylinder that is hollow, okay? But it's a cylinder because it's all the points that the x and the y are related because they have to satisfy the equation of a circle, and the z can be anything I want. Okay, so for example, I can pick a point in here. I can do the point, this point is going to be the point 3/5, 4/5, and 2, say. 3/5 and 4/5, when you square them and add them together, it gives you 1. So that point is in that cylinder. So is an easier one. This point is 1, 0, 0 is there, or this point right here, which is 0, 1, 0. But more generally, there's a lot of other points, and there's infinitely many points with different z values. So now what happens if I take that cylinder and I fix that z has to be 3, then it is a circle because now I have the, at z equals 3, I can draw the plane, and what I'm literally doing is intersecting that cylinder with that plane. So what I'm going to get is just a circle of radius 1 at level z equals 3. Okay? But if there are inequalities, then let me draw again the same thing I had before, like that. There is also now the z value is anywhere between 0 and 3, so I'm going to draw the same circle in here. But when z is 0 and x squared plus y squared is less or equal to 1, those are any point that has radius from 0 to 1. So it's actually the filled-in circle. It's not just the circumference of the circle, it's the filled-in circle. When z is 3, I also have a filled-in circle and anything in between. So now I have a solid can of tuna, something like that. Well, this is not to scale. It's taller than it's supposed to be taller than it is wide. So like a can of refried beans. Okay. So if you have inequalities, now with inequalities you can have solids. With equalities, it's usually just a surface of some sort. If I keep intersecting, I might going down to a point. But you can have anything from a solid, a surface, a line, a point, depending on how the intersections occur. Now, I can also compute distances in 3D. We had distance. I know how to compute the distance between 2 points. If I have x1, y1, x2, y2. Am I writing big enough? Yes, that's big enough for everyone. So I know how to compute the distance from here to here because I can use Pythagoras theorem. So if I draw a triangle there, then I know that this length from here to here and this length from here to here is, on one hand, this is x2 minus x1, and this is y2 minus y1. And therefore, by Pythagoras theorem, if I want to know what is the distance between those 2 points, the distance will be given by the square root of the difference of coordinates of the sum. Well, the difference of coordinates is square root. So that is the distance of 2 points in the plane. So what happens in 3 dimensions? Let me pick 2 points. Let's do some point that is somewhere here. And some point that is all the way, let's say, back here. Okay. So how do I figure out what is the distance from here to here? There's another big box one can draw just for those points, like this, and there is some box at that point is sort of like the big diagonal of a box, and the formulas just from Pythagoras theorem, we actually end up getting a very similar formula. If this is x2, y2, z2, and x1, y1, z1, it turns out that the distance is also the square root of the square of the difference of the coordinates. And you can prove that using Pythagoras theorem fairly easily. So that is the formula is given by, as I said, it's just a generalization of the formula in 2 dimensions. And we can use that. I will be actually posting these slides also. So I will download this PDF and post it. As you can see, my background is dark, so don't print it in actual paper. But I will be sharing these with you also. So let's try to find the distance between these 2 points. So the distance will be a big square root of 1 minus 1 squared plus 0 minus 3 squared plus 2 minus 0 squared will be the square root of the sum of the squares of the difference of the coordinates. All right, so this is the square root of 1 minus 1, that's 2. So 2 squared plus 3 squared plus 2 squared. So it is the square root of 4 plus 9 plus 4. 8 plus 9 is 17. So the answer, final answer, is the square root of 17. Right? Okay. Now, how do we find the equation of a sphere? Now that we know distances, we should be able to write spheres, because a sphere is just all the points that are equidistant from a given point. So we're fixing the distance formula. In the distance formula, we just have to fix this is equal to what we want the distance to be, and that should give me an equation. So let's try to figure out what is the equation of a sphere via this example. So I want all the points that are at distance 3, exactly 3 from 1, 0, 2. So that means that the distance, which is 3, has to be the square root of x minus 1 squared plus y minus 0 squared plus z minus 2 squared. Right? And if I simplify the things inside the square root, this is x minus 1 squared. I'm just going to leave it like that. I don't need to expand that square. It's actually convenient to leave them don't expand them. It's actually convenient to leave them like this. So this has to be equal to 3. So that's the equation of a sphere. Usually we don't like to work with that square root. So square both sides. And what you get is that the equation of the sphere, they're usually written like this. As the sum of 3 squares equals the square of the radius. Okay, so that is the equation of a sphere that is centered at 1, 0, 2, and the radius is 3. Any questions? So if I give you the equation x minus 1 squared plus y squared plus z squared equals 3, what kind of, whoa, it says a circle everywhere. That's supposed to say a sphere of, so it's a sphere of radius and center. What's the right answer? Okay, so let's solve it. So this tells me the coordinates of the center will be x minus the coordinate, y minus the coordinate, z minus the coordinate. So the center is 1, 0, 0. And just remember that over here, that is in the equation of a sphere, because we square that square root to find the formula. On the right-hand side is the square of the radius. So the radius, well, has to be plus or minus the square root of 3, but a radius of minus the square root of 3 would not yield anything. So it's plus the square root of 3. So it is a sphere, center at 1, 0, 0. So if I put 1, 0, 0, so right here, it's a sphere like this, and the radius is a square root of 3. There, so it looks a little bit like a sphere. All right, any questions so far?